Section 11.4 talks about geometry in 3 dimensions. So the first thing we have here is something called simple closed surfaces. And it says a simple closed surface has exactly one interior, no holes, and is hollow. Okay. So let's see. So it says, so these here are going to be simple closed surfaces right here. And then if you look here, it says these are not simple closed surfaces. Okay. So one of the reasons here, because we have holes, here we have two interiors, right? We got an interior there and an interior there. So simple closed surfaces, a sphere is one of them. So a sphere is a ball, right, like this. A solid is going to be the set of points of a simple closed surface together with all its interior points. And a polyhedron is a simple closed surface made up of polygonal regions and faces. The vertices of the polygonal regions are the vertices of the polyhedron. The sides of the polygonal regions are called the edges of the polyhedron. Okay. So here we have polyhedra. You can see kind of like little pyramids and figures like that. And then here are not polyhedra. Let's see. It says a prism is a polyhedron in which two congruent faces, the bases, lie in parallel planes, and the other faces, lateral faces, are bounded by parallelograms. Okay, so here's an example of what prism looks like. Okay, so oops, let me just come back up a little bit. All right, so this here is our prism. Okay, and so we have what we call vertices. Vertices are going to be these points here. Okay, and then edges. Let me change my color. Oh, come on, pen. Sorry about this, guys. It happens too frequently. There we go. Okay, edges are going to be exactly what you would think they would be. These are the edges, okay? These over here, these over here. And then obviously the faces will be like this face, that face back there, that one over there, the bottom, and the top, okay? Alrighty, so let's take a look at this first problem we have here. So again, vertices, guys, are points. Edges are going to be line segments, and faces are going to be planes, okay? So the first one here says list the edges of the figure. Okay, so the edges are going to look like this. AB, BE, so let's go like this. AB, BE, AE, right? Let's see, BC, CD, CF, that was DF actually. So DF, DE, and one more, AF. And so that looks like it's going to be choice B, right? Those are the ones that are my line segments, okay? Let's see. List the vertices. So remember we said the vertices are, right? The vertices are going to be the actual points, okay? So they're just single points, A, B, C, D, so on and so forth. Okay, that looks like it's going to be C. Okay. Now, here it says list the faces of the figure. So remember the faces are going to be things like ABE, the top face, right? The bottom face, CFD, okay? And then say this side over here, which would be ABCF. And then say this side back here, which would be AEFD. And then the one right here in the front, which would be BECD, okay? And if you notice, those are the ones that we have right there, okay? All right. So now we have a right prism, which our lateral faces are perpendicular to the bases, okay? And so these you can see are right prisms, right? And then we have something called an oblique prism. The lateral faces are not perpendicular, okay? So that's an oblique. Okay. A pyramid is a polyhedron determined by a polygon and a point that is not on the plane of the polygon. Okay, so here's our pyramid. Okay, we notice they all have the bases are the base is a triangle, and so are the faces. Okay, all right. So it says a simple relationship among the number of faces, the number of edges, and the number of vertices of any polyhedron was discovered by the French mathematician and philosopher René Descartes. If you've ever heard the expression, I think, therefore I am, this is the person who came up with that. And rediscovered by a Swiss mathematician named Leonard Euler. This is how you pronounce his name, Euler, like the Houston Oilers back in the day. Table 15 suggests a relationship among the number of vertices, V, edges, E, and faces, F, of any polyhedra. This is known as Euler's formula. Okay, so here is my formula right here. Okay, so here's our first problem, and it says, for the figure, find V plus F minus E, where V, E, and F stand respectively for the number of vertices, edges, and faces. Okay, so the first thing I'm going to do, we're going to find the number of vertices. So look, I'm just going to start putting my vertices so that we can count them. Okay. All right, so I have 1, 2, 3, oops. Oh, come on, pen. 3, 4, 5, 6, 7, 8, 9, 10. So the number of vertices is equal to 10. Okay. Let's find the number of faces. Okay. So the number of faces are going to be like the sides. So look, there's 1 on the top, 2 on the bottom. Oops. Come on, pen. There we go. Okay, 3 here, 4 here, 5 in the front, 6 on the back, 7. So we have 7 faces, okay? And then let's do the edges, okay? So the edges, so I'm going to go 1, 2, 3, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and right here, 15. So edges is 15. Okay, so now I'm going to go ahead and use our formula, V plus F minus E. So vertices was 10, faces was 7, edges is 15. So that's 17 minus 15, which is equal to 2. Okay. All right. So let me scroll down a little bit more. Okay, so it says, given the prism shown to the right, name the following. So we want to find the vertices. Okay, so let's do that first. A. Vertices. Remember, these are going to be our points, right? So look, I'm just going to start, I'm going to try to go, I'll tell you, the order shouldn't really be important, but look, B, K, A, F, V, and D. And those appear to be my vertices, right? Okay, now let's do part B. Part B are going to be the edges. Okay, now remember, the edges are going to be our line segments. So look, here's 1, BA. Here's 2, KF. Here's another one, BK. Here's another one, AF. Are these problems hard AF? Hopefully not. BV. And VA. Okay. And VD. And KD. And DF. Okay. So those are my edges. Okay. And let's do part C, which says, let's find our faces. Okay. So we're going to now find the faces. Okay. So let's do the top face. BVA. Okay. BVA. Okay, let's do the bottom one, KDF. Okay, let's do this one right here in the front, BAFK. BAFK. Okay. Let's do this one over here on the side, BVDK. BVDK. Okay. And let's do this one over here, VADF. Okay. And so we got our faces, okay? All right. So now let me clean up this mess, okay? And let's do part D. Part D says, where does the intersection of the face BVA, okay, so BVA, BVA, this one here, and the edge AF, where do they meet up at? At the vertex A. Okay. And then, let me get my eraser again. Let's clean this mess up. Okay, and let's do part E. Part E says, where does the intersection of the face BVA, BVA, and the face KDF meet? So let me do that actually in a different color. Let's go blue. KDF. So if you notice, that's the top slice and that's the bottom slice. So we would say since they do not meet, it would be the empty set, right? So sometimes, guys, that's a little symbol they use for the empty set, but it means that they don't intersect, right? Okie dokie. And it says, if one or more corners of a polyhedron is removed by an intersecting plane or planes, the polyhedron is called a truncated polyhedron. So we have a truncated square pyramid with parallel bases. We have a truncated cube, right? We looked at that a little while ago, and a truncated prism. And it says a cone is the union of line segments connecting the point P with each point of a simple closed curve, the simple closed curve in the interior of the curve. All right, so we have a right circular cone, an oblique circular cone. Okay. Let's see. Okay, so it says the figure on the right represents a card attached to a wire. Determine what the figure would look like if the card were revolved about the wire. So let's explain what that means. That means that we're going to stick this thing in the ground, okay? And then we're going to start spinning that little pole. If we were to spin that pole, we'd end up with something that's going to kind of look like this, okay? Right? So out of the choices that I have here, A, B, C, and D, choice A appears to be my answer, right? Okay. So look at the next one. We're going to do the same exact thing. So we're going to spin this pole, okay? So we're going to start spinning that right there. So what's going to happen is this is going to kind of do this number. That piece is going to look like that. And now look at my choices A, B, C, and D. We're going to have a cone. Okay. And we're going to do this again. Okay. We're going to put this thing in the ground and we're going to start spinning this thing right here. Okay. And this is what we're going to end up with when we start to spin that deal. And so we're going to end up with a cylinder. Okay. And let's see. Looks like we got a couple more. So I think we actually did this one already, didn't we? We'll do it again. It's okay. It's no big deal. So we're going to have an hourglass. Maybe we didn't do that one. There we go. There's my hourglass. And then, let's see. So we're going to start to spin this guy here. Okay. And this is going to kind of do that number. And so we're going to have our two joined cones, okay? And that right there, guys, is 11.4.